Now that we have discussed how to determine whether or not a discontinuity corresponds to a vertical asymptote or a hole, let's deal more with some asymptotes. Whenever we look at a vertical asymptote, we can determine the behavior around that vertical asymptote by looking at the exponent on that factor in the denominator. So if x minus c corresponds to a vertical asymptote, and the exponent on that is odd, then on either side of our asymptote, our graph does the opposite thing. So either we are decreasing toward negative infinity and increasing toward positive infinity on the other side, or we're increasing to infinity on one side and decreasing to negative infinity on the other. So the key thing is that an odd exponent will yield opposite behavior on either side of our vertical asymptote. An even exponent, on the other hand, would mean that there is the same behavior on either side of the exponent. So an even exponent would mean that we would have both increasing to positive infinity or both decreasing to negative infinity on either side. Now let's take a look at a warm-up to discuss horizontal asymptotes. So go ahead and pause the video and substitute 1000 in and substitute negative 1000 in for x in each case, and determine what the y value is that you would obtain on this function. So if you substitute in x equals 1000, what do you obtain? We will round our answer to 4 decimal places. So r of 1000 is approximately 3.0010. And if you substitute negative 1000 in, what do you obtain? $2.9990. So what's this mean? If you notice, 1000 and negative 1000 are extreme values of x. So 1000 would be way over on the right of our graph, and negative 1000 would be way on our left on our graph. And what we notice that as x gets very large or more and more negative, we are approaching 3 in both accounts. So if you notice, we have a horizontal asymptote of y equals 3. So as x approaches negative infinity, as x gets more and more negative, we're approaching 3. And then likewise, as x approaches infinity, we're approaching 3. In some ways, we can think of horizontal asymptotes as describing the end behavior of our rational function, because what we're dealing with are extreme values of x, so far to the left and far to the right. So when do we have a horizontal asymptote? Well, in this case, where did this 3 come from? So if we're looking at extreme values of x, what carries the most weight? It will be the first terms of each of this. We have 6x squared and 2x squared, and they have equal weight almost because we have this x squared and x squared. And so 6 over 2 is 3. One way to see this in a more rigorous way is we can multiply the numerator by 1 over x squared and the denominator by 1 over x squared. Then we would have 6 minus 10 over x minus 7 over x squared. And that would be 2 minus 4 over x minus 15 over x squared. And so if we're dealing with large, extremely large values of x, say x is 1,000 or x is 1,000,000, what happens to these fractions? This would be really small, meaning close to 0. This would be close to 0. This would be close to 0. And this would be close to 0. So we'd have basically something that's almost 6 over something that's almost 2, and we would get something that's getting closer and closer to 3. So let's formalize this rule. Here we have a rational function, which is a polynomial over a polynomial. Now notice, the polynomial in the numerator is degree m. The polynomial in the denominator is degree n. So the rule is, if they are the same degree, then we can just look at the leading coefficients, and the horizontal asymptote will be y equals the ratio of those two leading coefficients. And this corresponds to what we saw in the warm-up. Now what happens if the denominator has a larger degree? If that happens, then the horizontal asymptote is simply y equals 0. Let's take a look at an example. So let's find the domain of this function first. So we can factor the denominator as x minus 2 times x minus 1. We're going to set that equal to 0. The solution to that will be x equals 2 and x equals 1. So the domain would be negative infinity to 1, union 1 to 2, union 2 to infinity. Now, to determine whether the breaks in the domain corresponds to wholes or vertical asymptotes, we must factor the numerator. So let's go ahead. I'm going to write that off to the side. So r of x, let's factor the numerator, is a difference of 2 squares in the numerator, so x plus 2, x minus 2. The denominator we've already factored. It's x minus 2, x minus 1. And we can cancel the x minus 2's, and we obtain x plus 2 over x minus 1. Now, that's as long as x minus 2 wasn't 0. If x minus 2 were 0, then we couldn't have canceled. So r of x can be simplified to this, as long as we're not talking about x is equal to 2. So now, this means that we have a vertical asymptote that corresponds to the denominator, x minus 1. So x equals 1. And then we have a hole at 2 for the x value. But what's the y value? We substitute 2 into our simplified version. So what would have been there? 2 plus 2 over 2 minus 1. So 4 over 1. So we should have a hole at 2 comma 4. Now, do we have any horizontal asymptotes? Notice the degree of the numerator is 2. The degree of the denominator is 2. So, we look at the leading coefficients because the degrees are the same. So the leading coefficients are each 1. So the horizontal asymptote is y equals 1. So let's take a look at a warm-up. So we're going to use polynomial long division to rewrite this. So we can't use synthetic division because what we're dividing by is not in the proper form. So we have 2x cubed plus x squared minus 8x minus 4. And we're going to divide by x squared minus 3x plus 2. So we will focus on the first term of our divisor and look at 2x cubed. So what can I multiply x squared by to get 2x cubed? Well, I need to multiply the coefficient by 2, and then I need to multiply x squared by x to get x cubed. So that means that we're going to multiply by 2x. Now, we take the 2x and we multiply it by the whole divisor. And we obtain 2x cubed minus 6x squared plus 4x. And now we subtract off this whole thing from what's above it. And so we obtain 2x cubed minus 2x cubed is 0. Then we have x squared minus negative 6x squared will be positive 7x squared. Negative 8x minus 4x is negative 12x. Bring down the minus 4. Now, what does it take for x squared to become 7x squared when we multiply? And we just need plus 7. So we multiply 7 through the whole divisor, and we get 7x squared minus 21x plus 14. Again, we subtract. And so we get 7x squared minus 7x squared is 0. Negative 12x minus negative 21x will be a positive 9x. And negative 4 minus 14 is minus 18. And so we obtain r of x equals 2x plus 7. That's the quotient, plus the remainder over the divisor. So now, what we're going to do is graph r, and we're going to graph the quotient. Y equals the quotient, that is. So we're going to graph y equals 2x plus 7. Go ahead and do that. Graph r, and then graph y equals 2x plus 7. So I would suggest pausing the video, going to Desmos, and graphing. You should obtain, this is the graph of r, and now we'll graph, in addition to that, y equals 2x plus 7. And notice, I've made it dashed. To do that, you can go to Settings and then click here and change the color and the style of your line. And so, notice y equals 2x plus 7 is our slant asymptote. So, if I have a rational function, so the polynomial in the numerator is degree m, and the denominator is degree n, and notice m is 1 more than n, so the numerator has a higher degree than the denominator, but only by 1. So you can have an x cubed over an x squared, or an x to the 5th over an x to the 4th, anything like that. Then you can divide using synthetic division when you can, or long division when you can't, and your oblique asymptote, or your slant asymptote, will be in the form y equals the quotient.